All right, thank you all for coming. Thanks for the organizers for having me. My name is David Andrzejewski. I work at Sumo Logic, and I'm here today to talk a little bit about reliable machine learning and kind of broadly what are some of the problems and what are some of the solutions out there. First, really quick, just a little bit of context. Just if you're familiar with video advertising, there's a notion of a pre-roll. This is kind of what you're seeing through right now. Just some context, my employer, what we work on is a cloud-based data analytics platform, collecting logs, metrics, all these kind of events generated by your software at a large scale and doing some fun kind of data analytics with that. The basic idea is you can kind of capture all of this information, use it for ops, uptime, security, things like that. So if you are running a software-oriented business, as I imagine many of you are, this is something you might want to consider. From the engineering side, there's quite a bit of interesting data stuff going on there. Happy to talk about it sometime. Grab me in the hallway. So broadly, the focus of this talk. Ultimately, I don't think it's super controversial in this audience to say software kind of eating the world, software all over, software in everything, software your phone. However, it's also probably not controversial to say that very often the software is not so great. There's all sorts of bugs, vulnerabilities, dependency problems, supply chain attacks, different kinds of failures. If anybody tried to use the link, anybody local that PG&E sent out in the event of the wildfires recently, and that didn't work because their website had fallen over. If you recall the healthcare.gov launch, clearly, we as a civilization have not quite 100% nailed the efficient creation and authoring of super reliable software. And now we are also going to add machine learning to it. And so now we kind of have this new sort of tool in the box, new-ish, and it's kind of getting democratized and pushed out into more and more different kinds of software. And how is that going to make things easier or not easier? And I would claim for the most part, at this stage, it is not really going to be easier. So what I'm going to try to walk through is just kind of a survey of a lot of the different kind of pitfalls and some of the tools that are out there from an open source or commercial or services perspective that are at your disposal to potentially grab to kind of help deal with these new challenges. So, are ML systems challenging, right? And I would say, I'm not going to dig super deep into this, but this talk is going to be full of a ton of references, so when eventually we share out the slides, most of these things are linkable, searchable, Googleable kind of stuff. But if you talk to many, many, many folks, these are kind of considered sort of iconic research papers out of Google in the cataloging of the sort of pitfalls and problems that you can kind of hit trying to build practical data-driven, machine learning-driven systems, right? You are going to have new ways of coupling your system. You're going to have new feedback loops. Potentially when you're experimenting, you're going to have a lot more iteration, dead code, dead prototypes, changing the features. There's a whole kind of avenue of new ways to couple things. And so that's kind of the high interest credit card of technical debt paper, which is well worth your time. And kind of a sort of spiritual sequel to this is this like ML test score paper. And a lot of these ideas are going to come up throughout this survey of what does it mean to actually have a tested ML system. And this kind of extends all the way from your data, the features, the feature generation code, your actual modeling code, your modeling, serving, deploying code, testing the tests, everything like this. So as kind of a starting point, this is a great place to start to really understand, okay, what are some of the challenges, and we'll dig into it a little bit more. And yet another one, kind of on some parallel track, is rules of machine learning and these other kind of best practices. And if you read this, what's really jump out at you there is very much emphasize really just stitching together an end-to-end thing in the simplest possible way first, and then kind of building up on top of that. And that's going to kind of come again as sort of a consistent theme in this discussion as well, is if you cannot sort of make the very, very simple thing actually work or actually be kind of reliable or test that, when you create the most sophisticated possible thing with the really elaborate feature logic pulling from 5 different data stores and feeding into a brand new deep learning model, you're going to have big problems. And so there's kind of a sort of agile, almost kind of approach advocated in this paper. So let's assume that we're going to buy that it's challenging. And now why? Let's try to understand a little bit how we could think about this. And sort of given this conference and this venue, one way to think about it is kind of from a functional perspective. And another talk and slides I'd really recommend talks about kind of how types and tests compare in terms of constraining or defining what constitutes a valid implementation of a function. And this gives you like a very quantitative way even to think about what does a given function do. And again, at this audience, probably the type sort of approach is going to be kind of compelling. But if you take this first function that goes from a string to a string, how many different possible implementations could you have? Right? Ludicrous number. And you're going to rely probably on unit tests and other sorts of constraints in your behavior to try to narrow it down to some subset that actually does what you want. Whereas by, let's say that you have some kind of enum-like structure, and you have a second function that just says, is it a weekend? And it just takes something from the enum structure and maps it to a Boolean. This is obviously a super trivial example, but it's meant to kind of sketch out the two extremes of this continuum by kind of looking at it from this sort of type, how many different possible implementation perspective. You can say that being confident in the correctness of the second one is going to be a lot more straightforward than being confident in the correctness of the first one. So let's put on our types versus test hat and look at machine learning. And so one kind of classic way to think about the standard supervised setting of machine learning is that you have a function, a training function, that maps a collection of training examples. So this could be input X is your email, output label Y is whether or not it is a spam. And you want to learn a function that maps from new X that you might see, new emails, to predicted label of spam or not spam for those new emails. And we can kind of take the same tool for thinking about it from the previous slide of how many possible implementations of that function are there. And actually an entire sort of swath that if you're interested in this kind of thing, I'd recommend to check out in statistical learning theory is basically looking at different model classes and how many different ways they can instantiate that function. And you can have something that's super kind of constrained, like say a linear regression or just a one-dimensional threshold, something like this. There are relatively few ways you can separate data sets, and so it takes fewer examples to learn, whereas an arbitrary universal neural network kind of thing potentially has a higher quote-unquote VC dimension and is going to be able to split up many different data sets, and it's harder to learn because there's more possible correct implementations. So that's a single machine learning model, but when you are building a machine learning kind of system, you are actually learning a function, or you're implementing a function that will emit a function like this. So we go from having many possible implementations of that predictor to the power of many possible implementations of your software for emitting that predictor. And so this is just one kind of way to bring a lens onto why this is going to be really challenging. And in fact, it's actually worse than that because you have hyperparameters. So if you ever use any of these libraries, sklearn or similar, you're going to see a whole bunch of arguments that have these handy-dandy default values. But all of these typically mean something quite reasonable. And they're sometimes called hyperparameters. And so actually you have to say, I have a learning approach, and I want to set the hyperparameters, and I'm going to output this. And that becomes, and even blows up the space of possible implementations even further. Now, this is kind of what the Google paper is often talking about. It can actually even be much, much worse than that. So this training data probably is coming to you from the outside world. And your predictions, hopefully if they're having an impact in driving the product and doing something useful, are also going to go out there in that outside world. And potentially, there's going to be kind of feedback loops and things like that, right? So this kind of phrase has to do with Wall Street, an engine, not a camera, and the idea of sort of machine learning models. One sort of school of thought is it's just a camera that captures facts and captures regularity about the world, and that's that. But the other one is that actually the models, as people interact with them and game them, are going to drive and change behavior. And so anybody who kind of works in this sort of relevancy or ad tech or this kind of thing, the output of your model, the output of your recommendations are going to affect behavior that is going to be used as training data in your further recommendations. And this is something else that's really called out in the Google paper. So I hope I now kind of convince you this is some non-trivial sort of software engineering challenges. We can kind of lay it out a little bit as a map of potential problems. And a lot of these, again, kind of map to the structure or the outline of that Google high-interest credit card debt paper. But upstream, you probably have a data pipeline that's getting this data from somewhere. You can just have straight-up bugs in the data pipeline. You can have changes in the data pipeline if it relies on outside data sources that your team or yourself don't control. You can just have dirty data, incorrectly kind of captured or instrumented stuff. Then you're going to learn a model from it. Maybe you picked the wrong model. Maybe your model has weird failure modes. You're going to serve these results. Now, they might not actually make sense to people, or the model you chose might have a big gap between what that model emits and what kind of the actual end user wants to consume. And that's kind of gets into this last phase. Ultimately, for the most part, and with very few exceptions, your customers, your end users, are not consuming the output of a machine learning model raw. You're not doing decision tree as a service. Probably there's some sort of last mile user experience wrapping and things like that. And that's another place where you could have some potential for serious problems and headaches. And of course, there's always the loop back. In software engineering, machine learning engineering, you're always kind of iterating back and forth. And this is yet another place where you can have some problems. You've changed the features in your serving layer, but not your training layer. Reality has actually changed out from under you. Different behaviors are kind of coming in on your data, or your upstream behavior is different, or you've just introduced a code regression. So this is kind of yet another way that you can sort of have some more problems creep into your machine learning software system. And all of this, by the way, of course, assumes that your sort of base 101 level software actually just doing what you would hope anyway. So that's, on top of this, you have these other challenges. So what kind of tools do you have at your disposal? Right? We're going to walk through some of the possible portfolio you can kind of build of approaches and solutions to at least limit some of your risk and exposure to these problems. So this is a really funny kind of anecdote from the genetics research community. And so I don't know if folks have worked in kind of genomics, genetics, or biomedical informatics, but you have all these genes and you have their names and there's sort of these code words all over the place. And they're often just kind of a jumble of letters and maybe some number. And these actually refer to genes in humans or other model organisms. And like many people, biological scientists using Excel. And actually they were having an issue where Excel was automagically suggesting that particular gene names are actually dates. Sept2, which is some gene, is actually being interpreted as September the 2nd. And so this kind of bug, you may or may not be yourself working on genetic data, but this kind of thing can happen all over the place, and actually apparently was happening 20% of the time to various people. So one possibility here is to actually consider your data pipeline within the scope of test coverage and automated test coverage. And this one particular instantiation of this idea is an open source library called Great Expectations. And basically you can think of this as a sort of monitoring or unit testing for your data. And you would kind of bake this into your data pipeline potentially and assert certain conditions or invariants against this data, and it will fail like a unit test against your code. And so an example test assertion would be something like this. And this is from their documentation, and they walk through this sort of classic Titanic survivor data set and passenger class. And you can basically say, this column, it's going to come in as a string because it's coming from some other pipeline or SQL database or whatever. And I expect only ever to see these three particular values, these three particular strings in that column. And so if you have something that you are considering to be kind of an enum style piece of information, but is coming to you from some upstream place where it's encoded as a string, you can kind of encode this sort of set constraint and say, I only ever expect this column to take on passenger class as first class, second class, third class. If I see a calendar date, if I see somebody's name, if I see an empty string, I want my pipeline to throw this error, and you can kind of run this against your data pipeline as it flows through. And there's an entire library of sort of similar assertions. I expect this to always be a number. I expect this to be non-negative. I expect it to be this, that, or the other thing. So in basically building this into your pipeline is one way to kind of protect against some of those upstream sort of dirty data sort of failure modes. Kind of sort of just a bunch of jumbled keywords. There's a whole universe of research going on right now. It's a very hot kind of academic topic that I'm not going to really have the time to dig all the way deeply into, but making the model itself more robust and resilient. So you can say, I want my data to have these certain characteristics. I want my software and outputs to have these other characteristics. But this research sort of says, for given model classes, model learners, and actually the model itself, how can we ensure that the model is not going to have extreme failure modes in the presence of certain kinds of attack vectors or failure modes? And so what I mean by that is you misspecified the model entirely. So this might be in the case of a probabilistic graphical model, and you've just got the wrong model for the data, and you have dependencies where there shouldn't be, or vice versa. How badly is the performance or output of that model going to be degraded in the face of you slightly misspecifying, choosing the wrong machine learning model. Another one is data set shift. So there's kind of a classic machine learning AI story of DARPA working on this tank detector that would take an image and tell you if there's a tank in it. And it seemed to be getting 100% training set accuracy and all this great stuff. And then they actually tried to field it, and it was an utter failure. And it turned out that the tanks were always either in front of a forest or it was daytime or something like this, right? But basically there was a data set shift where the images of the tank from the training set were always in front of the forest, and all of a sudden in the test set, they're not in front of the forest. And of course, the just dumb statistical machine learning model did not kind of anticipate that data set shift. So that's another kind of degree of robustness. To the extent that the real world or the actual data does not exactly come from the same distribution as your training data, that's another kind of challenge that your model is going to have to face. And how do you bake that into the model itself? Another one is this sort of adversarial case. So this is the notion that you're going to have potentially an adversary who can tweak data in particular ways and cause your model to give very extremely different outputs. And the sort of the research papers on this, the example they use, there's pictures of pandas and pictures of stop signs. And because of sort of the nature of how a deep learning model works, they're able to inject some very targeted noise and get it to completely fail. And so how do you create a model that's a little bit more robust to that? And sort of the last kind of class is sort of sensitivity to outliers. And this is the case where if you say, I want to fit a line to some data, if you're doing standard ordinary least squares and you have one data set or data point where the data is just kind of arbitrarily far from the line, it can drag your linear fit arbitrarily far in that direction if you're just using sort of a normal squared loss. And there's a whole kind of universe of research going back many years on how to do that, but basically some updated thinking for that. How do you have individual dirty data points or misspecified data points or just straight up malicious data points not throw off your model in a fundamental way? And so there's a whole ton of academic kind of research about that. Calibrated predictions are another thing that's going to make your actual model a little bit easier to understand and interpret and work with respect to your rest of your system. So this is from the scikit-learn docs. And basically the idea of calibration is if I output 30% probability that it's spam and put all of those in a bucket, will 30% of them actually be spam, right? And this is a property of particular modeling classes or post-processing of models, that they have outputs that can be interpreted as genuine probabilities, as opposed to just a score, high score equals spam, low score equals not spam. Can it be interpreted as actual probability? This is something else that's going to make it easier to kind of work with. And of course, just kind of sort of standard software engineering advice is that if this is not your core thing that you're doing, if possible, you can kind of buy or borrow or open source instead of building your own. There's actually a super interesting talk yesterday about this Onyx machine learning representation framework and how to serve it from Scala and things like that. Of course, all the cloud providers would love to sell you their kind of ML as a service. But if this is not the core kind of thing you're doing, this is a great way to avoid shooting yourself in the foot in a ton of different exciting ways. So now kind of 3 T's of reliability potentially. How can we use these kind of tools, types, testing, and monitoring to kind of enhance the robustness and reliability of the overall machine learning kind of setup? So of course, can types help? Again, with this audience, probably I would guess folks kind of inclined to think yes. But much like standard software engineering, you want to let the compiler test catch some of these errors for you. So very often in machine learning pipelines and such, this is a really trivial example, but you're working with time and just passing longs around your code base. Is it a day? Is it a millisecond? Is it a year? It's really easy to have really wild kinds of bugs. Whereas if you're actually using the sort of proper library support, or you kind of constrain and baking it into the data types themselves, it's going to be a lot harder to have those kind of problems. And again, back to that types versus test thinking, you dramatically sort of constrain the universe of problems that you can cause yourself. So one sort of interesting data point in the space of how you can use types to sort of enhance the reliability or correctness of your machine learning pipeline is the open source Salesforce machine learning library. And what they've actually got here is a pretty nice, sort of well thought out kind of schema for how to think about different types of features. And to the extent that you have this kind of baked into your pipeline through your training, your testing, your serving, your ETL, it's going to make it a lot harder to sort of introduce bizarre mistakes where you are interpreting times as some other numerical quantity, or you're interpreting I quoted number as an actual string or things like that. So this kind of forces a little bit thinking and effort upstream, like many kind of type-based solutions do, but at the kind of advantage of avoiding a whole sort of class of interesting failure modes. Another sort of thing that's its own whole talk that I talked a little bit about last year here at this conference was you can do information flow control with types. Why this can become relevant in a machine learning or data science context is you might have certain information that you don't want kind of bleeding or leaking from training and validation to your actual test set, or bleeding from the future into the past, or all sorts of other ways that information kind of flow through your software system in a way that's going to cause you to kind of fool yourself about how well your machine learning model is actually performing. And actually the context that I was interested in when I had sort of talked about this last year was data privacy and sort of sensitive information control. Often machine learning systems are being trained and run against data associated with actual users or customers, and to the extent that you don't want individual R&D engineers poking around in that data, or that data leaking through your software system out to the outside world in some way, you're handling sensitive data, you can kind of bake into the type system, tell me that this data is sensitive and I don't really want it to kind of go in different places. So you can check out that talk if you're interested in that. Testing. So, of course, we love when computers can do work for us, and we'd like to test our machine learning models and be pretty sure that they're doing what we want. However, there's some extra challenges to testing machine learning models often. You might have non-deterministic or very unstable behavior on any individual data point. So it becomes a little bit harder to unit test. This one data example should be X, Y, or Z. Also, these labeled examples are potentially really expensive, and you actually want them in your pipeline being used for training anyways. And how can we kind of get around that? So property testing, this is just not necessarily a machine learning thing as such, but just general sort of framework for doing automated testing where the computer is going to do something useful for us. You just assert that there's a property that my function should satisfy for all inputs. So for example, I could say I want to do ordinary least squares for all weights that I learn from any data set X. I want to have that it converges to a valid parameter vector. Okay, and a kind of constrained version of this would be that I want for any input data set that has no nada numbers, no infinities, sort of well-formed data set, my ordinary least squares machine learning training should converge to a realistic output vector. So what this actually kind of means in practice is you can use these fancy property testing libraries. They will auto-generate nice test cases. You can have combinators for sort of building these test case constructors. They will shrink examples down to the minimal failing case, do all sorts of nice stuff to help you have automated testing on your data. But where this really kind of comes potentially into machine learning is this metamorphic testing idea. So this is something really interesting where supposedly the claim of these researchers is you can kind of alleviate the oracle problem. Where do I get the labeled data? So based on the name, it kind of sounds like something that belongs at this conference. But the basic idea is you want to define these metamorphic relations that hold over sequences of inputs, outputs. The library or the implementation, the testing can then automatically transform the inputs and just check that the relation holds over the outputs. So you don't actually have the output label, you don't actually have the ground truth output, but you know that if this input came to this output and I tweak the input, I should expect the output to be tweaked in a certain way. A little abstract, some specific examples, and this is from the Chen survey. Say that you have a database query. Adding a disjunctive term should only ever increase the number of results returned. So actually the output should be a superset. It might not be proper superset, it might just be the exact same, but adding that disjunctive term should only ever result in more results. The shortest path in an undirected graph from A to B should be the same as B to A. And there's all sorts of a huge universe of kind of testing, programming language research in this area where you can see kind of what they were able to do with it. So, pulling it back to machine learning. One big challenge, again, in machine learning is it's really hard to test and verify that your implementations and your systems are kind of doing what you think. So, and especially in unsupervised machine learning. And so there's a really cool paper where they are basically saying, how do we define metamorphic relations and do interesting testing on clustering, which is kind of a notoriously difficult to evaluate sub-approach of machine learning. And just really hand-wavy here, clustering, basically, given a pile of data, break it into a few different piles. That's the clustering problem. And what you'd like is that within the piles, the points are very similar to each other, and the piles themselves are dissimilar to each other. So thinking about kind of spatial representation of fixed length feature vector. In this case, maybe we have all of these little circles, and distance function, we've clustered them into these little clumps that sort of correspond to a human interpretation. Now, say you've got a clustering implementation, how can we use metamorphic testing to test it, right? And the authors of this cool metal paper define all of these metamorphic relations that should be expected to hold over clustering. A lot of very kind of standard stuff where if you translate, rotate, shift these feature vectors, they kind of do what you think. If we shrink points towards the centroid, they should stay assigned to that centroid. If you add extra dimensions that are totally redundant with respect to the existing dimensions, it shouldn't affect the outcome. If you add outlier data points, it shouldn't affect the clustering of the inlier data points, and so on. So there's kind of a ton of different ways you can say, without having ground truth data, you can just say, is my clustering algorithm sort of robust, or does it behave as I'd expect in these different ways? And so these are the key references. Again, I'll kind of send it out later, but there's some really cool stuff there. All right. Managing the life cycle, I guess maybe I'll go over this really quick, but everybody uses, I'm assuming, source control and stuff for your source, right? And likewise, there's a whole new universe of tooling from open source and commercial side to basically try to do similar thing with models, including some folks who are actually here. They've done some cool stuff. Monitoring, you want to basically stand up, look at these input features and output features and see, are they actually behaving like we expect? This is kind of a whole universe. If the input fields change dramatically, you want to know about it because it might cause the way your model behaves to change dramatically as well. Actually now I have, say that you have some individual model output, I want to be able to explain it. This is another huge area of research. One of the most popular papers sort of recently here was Lime, and if you're going to try to do a literature search on this, I would kind of anchor your search there and look for more recent work that cited Lime. That would be my sort of research hack to find some of the cool new research here. But the basic idea is, say that your image classifier has classified this image as class X, or has classified this document as class Y. Why? How? Like, which fields were the most salient in terms of the model making that prediction? And once you're trying to investigate problems with your model, your pipeline, your data, everything, those kind of more granular debugging explanations can be super valuable. And of course, there's a whole bunch of people working on this research, open source and commercial as well. All right, coming up on the end. So say that people get very unhappy when machine learning systems do not work well. And there's actually some really cool psychological research where they are really, really unhappy. In fact, more unhappy than they would be if they thought a human screwed up that way. So humans are kind of willing, in this kind of psychological research, to cut other humans some slack. Say, they'll do better next time, they'll learn from their mistake, and so on and so forth. Whereas the computer screws up, you are furious. There's no coming back from that. And so what can we do about it? So they actually did some follow-up research where they determined that if the user is allowed to tweak or tune the output a little bit, they become dramatically more forgiving, even if these tweaks are like really, really small in scale. So the implication is you should give your user some levers or knobs to correct or adjust those outputs. And so, kind of example we actually have in the Sumo Logic product, we cluster your logs, but if you don't like the cluster, you can kind of explode it into smaller clusters. And this really kind of helps people feel better about it. So I'm running out of time, so I'm gonna go a little quick. There's one kind of case in which sort of, in academic machine learning AI, the incentive is to kind of pull more and more of the problem into the model. And when you're actually trying to build an industrial system, this may or may not be a great idea. Actually, you might be better off thinking of your model as a small piece of a more isolated, or a small isolated piece of a more coherent, larger system. And you could potentially sort of fix the mistakes or post-process your model in different ways to kind of get a better shot at it. And you might actually want to sort of enforce sanity checks or things like this. You can add some domain knowledge, put wrapping logic around your model to avoid these kind of mistakes. All right, the very last thing, the legend of the Russian space pen when not to use machine learning. So this is a fun story, not actually true. So the problem is that your pen doesn't work in space, zero gravity, so NASA spends $1 billion and develops a space-age super pen, and Russia uses a pencil, right? And the meta lesson here, why it should be true even if it's not a true story, is you can always redefine the problem. And this is especially a big problem in machine learning because machine learning data science people are always looking to phrase problems as machine learning problems, even if they are not necessarily problems. Because sometimes it really pays off. So this is a really cool database paper from Google where they take previously a not machine learning problem in databases, turn it into a machine learning problem. And this is a thing that people think is a face on Mars, right? Or the moon rather. And they, actually I forget if it's Mars or the moon. But the problem is that as a machine learning person, you see machine learning problem everywhere. So say that I have latent users on Netflix, I want to demix your profile. Very cool machine learning profile problem. There's 3 people in a family, they're all using Netflix. Who's viewing what? Let's do it with machine learning. No. Netflix just asks who's watching. In machine learning, like operations, as Sumo Logic, for example, people want alarms to not go off for their system when you're having regular maintenance. Can we auto-learn the maintenance? Can we detect the seasonality, do a fast Fourier transform, do an econometric sort of seasonality prediction? Or more likely, probably what you'd want to do is create an API that just lets the user say that maintenance is happening, and they can put it at the front of their maintenance script, right? And so one last kind of thing, the best machine learning that you can ever have is when you don't have to do the machine learning. So despite kind of your interest and skills, I would definitely encourage you to also think about it that way, is where is the Russian space pen in any given problem, right? So final takeaway, very boring, exercising eat your vegetable. There's new failure modes in machine learning. There's still no silver bullets, but hopefully I kind of give you a survey, an overview of how you can build a portfolio of approaches to kind of get a more reliable end system out of machine learning. So thank you very much.